Steven Rieder as our seminar speaker. So Steven, as you might have guessed from his name, is from the Netherlands. He did his PhD at the University of Leiden in 2013, if I'm not mistaken. And then he went on to do 1 year postdoc in Groningen. And then he moved out of Europe. He went to Japan at Rieder, where he stayed for about 3 years, I think. And then he came back to Europe, did a postdoc at the University of Exeter, and now he is at the University of Geneva, as you can see. He is a co-developer of AMUSE, and that's also what his talk will be today. Please, David, you have the floor.
Thank you. Yeah, so for the people who we met this morning, there will be a little bit of overlap between what we discussed and what I have in my presentation, but repetition is good, right? So don't worry about that. Yeah, my talk is about simulating star cluster formation. This is one of the main things I'm interested in. I was working on this at University of Ekster primarily, but I also continue working on this now that I'm in Geneva. So let's go into it. Basically, in my talk, I will sort of address 3 parts. The first part is going to be mostly about AMUSE itself, what it is, what you can use it for, and why I think it's cool. The second part is about a code that I developed using AMUSE, which I call Ekster, which is why I have the picture of this bird here. And the third part is really about results that we got from these simulations. So to start, what is AMUSE? The name AMUSE stands for Astrophysical Multipurpose Software Environment, and it is a tool for doing simulations in astrophysics. It is developed for doing multi-physics, multi-scales type simulations, which means there's more than one thing going on more than one scale, or one of these two. The project has been going since 2009 already. And mainly it is a Python interface to community-written codes that have been developed either recently or long ago. The origin of AMUSE is from the question, how can you address more than one aspect? How can you address more aspects than were originally intended in a code? So you have many people who've worked on n-body codes, many people who've worked on stellar evolution codes, and they were all interested in saying, okay, I want to go to the next level, introduce stellar evolution in my n-body code, or vice versa, introduce gravity into my stellar evolution code. But the problem is that if you extend monolithic codes, which are codes that are focused on one thing, it will generally lead to one of these aspects being better developed than the other. The other will sort of be an addendum, which leads to problems, usually. AMUSE is sort of the best of both worlds, where we combine these codes together to work in a collective framework. And we also have this nice picture of Simon in there. What AMUSE offers is that we have, for each of the domains that we support, which are gravity, hydrodynamics, stellar evolution, and radiation, we have at least 2 different codes for each of these domains. Nowadays, it's generally a lot more. And each of these codes will have a similar interface in Python. So the interface will be almost the same. You can basically switch out one code for another with one line if it's in the same domain. So that is, if you want to, for example, do a star cluster, first you develop with a tree code, then you want to do it a little bit more accurate, you move to direct embody code. That is very easy to do. It also allows you to do multiple things in one simulation, taking feedback from one into account for the other. So you can say, okay, stellar evolution will tell me that the mass of the stars is changing over time, and the stellar gravity code takes that into account. That's a simple example. Some other nice examples, nice things that AMUSE offers is that you can do rapid prototyping, which means that you can write a simple script in a very short time. To make it more complex, of course, can take much longer, but writing a simple script can take very little time. Nowadays, it's also quite easy to install. You need some prerequisites to be installed on your computer, like a compiler. If you do, then you can just do things like pip install AMUSE or AMUSE framework if you don't care about everything, and that will install it. Development and everything is going on GitHub, and it's a very open community, so that's also one of the things we like. AMUSE offers a lot of different modules. One of them is for initial conditions. We have a number of initial conditions that we can generate from AMUSE, for example, for the masses. We have a mass distribution for salpeter mass function, Krupa mass function, any kind of power law that you like. For standard cluster distributions like a plumber or a king model, or a fractal distribution if you want to start from an earlier age. For molecular clouds, for planetary systems, so lots of different ones to choose from. And if you have access to IOP science books, which probably you have at university, then you can download this book, which Simon wrote with Steve McMillan. And this book has many examples for AMUSE in it, and you feel free to look at those and copy them and change them and republish them if you like. Currently, we're working on version 2 of the book. Hopefully, it will be out later this year. And you'll hear when it's there. Here's a simple script for AMUSE. Here, what I'm doing is I'm setting up a system to simulate star cluster dynamics, star dynamics. I'm importing a plumber sphere, which is very simple spherical distribution of stars. I'm setting up the code called Hermite, which is a fourth order Hermite integrator. And I'm then integrating 1,000 stars for one n-body time, which is a time unit, internal code unit for time. And that's what this script does. Now, if I want to change this to use the BH3 code, which is a faster but less accurate code for larger systems generally, then this is all what I have to change. All the red lines are the only things that I changed. And the rest works exactly the same. It doesn't give the same result, but it works the same way. Now, if I want to scale this to physical units, so here I've been using code units, then this is what I need to change. So I also import units, which is a package that contains physical units like kilograms and meters and solar masses, etc. And then I say, okay, this cluster has a fixed size and a fixed mass, and it is evolving for 1 meg-year instead of 1 time. And then the rest works exactly the same still. In AMUSE, we also have multiple modules for stellar winds, visualization, and lots of other things. So whatever people have thought was helpful is probably there. If it's not there yet, then feel free to contribute. And one thing that we also do, and that's very important, is that we have coupling between codes. The simple version of that is done with channels. So a channel is something that says, okay, these are the particles in my code, and these are the same particles in AMUSE, and synchronize them. So copy all the values from the code to AMUSE or back, or from one code to another or back. And this is how you can do this. So you create a channel from the stellar evolution code to gravity, and you copy the mass and the radius, because those are likely to have changed from stellar evolution, and gravity cares about them. If you want to do more complex coupling, like between hydrodynamics and gravity, then you can do that with the bridge module. So here's an example of that, where we set up a bridge. This is called system, and we add 2 systems. One of them is called gravity, which is the stellar dynamics, and the other is hydro, which is the gas. As partner, they have each other. So that basically means that hydro is going to change what's happening to gravity, and gravity is going to change what's happening to hydro. So they interact on a certain time step, which I define then here. So this is very important. Bridge, oh actually this should have probably been one slide earlier. This is how it works. You do a kick for half a time step, then you do a drift for a full time step, and then another half time step kick, which is like a leapfrog integrator. And this was published in the Fuji 2007 and then later the Portuguese Wart 2020 paper. Like I said, it is a very open project. A lot of people have contributed, many more than I list here, but these were the main people listed in somewhere, I don't remember where. But yeah, we very much welcome contributions. So if you think, oh, I actually think this is interesting, but I'm missing this particular code, like a stellar atmosphere code we were just talking about, then we very much welcome contributions. Again, I'm ahead of myself. This is what I was just saying, right? Almost all codes are supported in principle, all languages, as long as your code language supports MPI, but that includes C, C++, Fortran, Python, Java. If your code is written in a different language, then I'm interested because we don't see that much. But suffice to say, generally it would be supported. An interface is basically a thing that just queries your code for what's there. So instead of just running your main program, we compile your code as a library and then say, okay, tell me what is parameter X at this point, or parameter Y, or the mass of your star, or the luminosity of your star, or the time. And this is doable for almost every code that we've come across. So that's AMUSE. Now, what I'm using it for myself is the formation of star clusters. So star clusters, as you know, are groups of stars with very similar ages. They generally form, well, in groups. They can be detected at very large distances in faraway Milky Way galaxies, in our own galaxy, of course. They're used as tracers for star formation, and they teach us a lot about galaxy formation. So how can we study them? Well, you have people who do observing. I'm not one of them. You can observe them in our own galaxy, nearby galaxies, then you can still see individual stars. Or you can look at distant galaxies and then you see them as integrated light. What you can also do is simulate them, and you can do them either in isolation, so just look at one cluster and simulate that, or you can simulate them as part of a larger environment, like a galaxy. And that is sort of what I'm focusing on here. Now, if you look at an example of a star cluster like Westland 2 here, you can immediately see that this is not a simple thing, right? There's not just gravity going on there. You can see that there's clouds nearby. The stars are all different. You can see that there's sort of these pillars of creation going on. So there's a lot of different physics that are important here. You need to look at both at gravity, you need to look at hydrodynamics, stellar evolution, and feedback as well. Now, I'm focusing in this talk only on the first two, really, just gravity and hydrodynamics. Stellar evolution is sort of included, but it's not really important on the timescales that I'm looking at. So that's graded out. Also, you need to think about multiple scales. So a cluster in isolation is just, one spherical thing, at least if it's a little bit older. But star cluster formation occurs on the scale where it also cares about what's going on outside its own little parsec or a few parsecs. the clouds that form the stars are formed in a galaxy. And the galaxy is quite a lot bigger than the star cluster. So this is a multi-scale problem. Now you can look at this in multiple ways. You can say, okay, I'm just going to be interested in different clouds. I try to form some clouds with turbulence, without turbulence, different shapes, etc. And model them and see what is important there. And that tells us a lot about these individual clouds. What I'm doing here in this work is I'm going to look at the different clouds that form inside one galaxy, and so not any specific clouds that I've modeled in some way. The problem is, of course, that if you want to do this in the ideal way, which is to model an entire galaxy, that's not doable. You have either too low resolution to say anything, or at least on the scale that I'm thinking about here, or you need a too big computer that just doesn't exist. So this is a problem. Yeah, the larger environment is something that looks like this. So here we have a picture of the M51 galaxy, where you can nicely see that there's these spiral arms in which all the stars are forming. You know, the red regions are young cluster regions. Yeah, so if you want to look at where star clusters are forming, that we need to know where that's happening. So to do this, we need to first see, okay, what do we need for this? So we decided, okay, we're going to take the SPH code Phantom, which many of you here know. It's a modern, reasonably fast and modular code, which made it nice for implementing an interface in AMUSE. It is not multi-scale. The gas particles in Phantom all have a fixed mass, which makes it fine for doing one scale, so one molecular cloud or something. But to also include a stellar wind in there is going to be difficult. And to look at both the galaxy and the cloud in combination is also going to be a little bit difficult. Also, Phantom is good for doing just gas particles. It has a tree integrator for that, so it's n log n order speed. But if you have many different individual stars, then this will really slow things down, because that's going with an n² law. So what we do is we use a different code for the gravity of the stars, which is PTAR from Longwang 2020, which is a great code because it does direct n-body gravity for stars that are nearby, but reverts to a tree code if they're far away. So it's a very much faster code than just a normal n² code. But it does not do hydro, so that's what we use Phantom for. Yeah, so instead of building this into one kitchen sink code, we use AMUSE. But we use, we start our initial conditions from taking a galaxy model and taking a part of that where we see that molecular clouds have formed that are going to form stars. We used the SPH code to handle the gas, and then the PTAR code to handle the stars, and we combine them with bridge that I explained before. Stellar evolution and feedback is a sort of wish list. So I developed the Ekster code for this. The name comes from, the bird, the magpie, which is sort of known for taking nice things, you know, and collecting them and putting them in its nest. It's sort of what I'm doing here. What we do with this code is that we first we take initial conditions from a galaxy simulation that's already been done. We zoom in on those, so we increase the resolution, and then simulate that region with SPH, n-body, star formation, and stellar evolution. And we wrote that with AMUSE. So a very highly simplified version of Ekster is like this. First we set up the system, so create the initial conditions, and then we say, okay, evolve this until we reach the end of our simulation, or until we don't care anymore. Okay, the time evolves, then we synchronize the models to the code, so that the codes are all aware of what's been going on. Then we evolve for some time, then we synchronize back, then we say, okay, do we need to form sinks, which are star-forming regions, really? If so, then we also try to form stars, we write our snapshots, and we make some plots. So the setup system works like this. First we create this converter, which says, okay, this is our time step, this is the length scale that we care about here. We add our gas and star codes to the system. We also include a tidal field, because the original galaxy that we were looking at was evolved using an external tidal field. Then we say, okay, bridge must know that our gas and our star code are affected, in fact, by each other, but also by the tidal field. And the tidal field is actually time dependent, so we also add that, but it doesn't have any partner. It's not being changed by any of the other systems. For synchronization, from the gas, we care about the positions, the velocities, internal energy of the gas, the density, the smoothing length, those kind of things. For the stars, from the gravity, we just care about positions and velocities. Stellar evolution, we care about the masses, the radii, luminosity, temperature, those kind of properties. To gas, that's the reverse. So we basically look at what may have been changed by something else. So again, this is positions and velocities and internal energy. And for the gravity, it is also the mass and the radius now, which may have been changed from stellar evolution. And that's what we synchronize every step. Forming sinks, this is where we are getting into more interesting bits. A sink in code terms is sort of like a particle that accretes the gas onto it. So when the gas is sort of collapsing into very short orbits around each other, so you say, okay, now we just aggregate that into a sink. In terms of physics, a sink doesn't really exist. It's not a real thing. In terms of my simulation, I use it as a star-forming region. So a sink contains a mass. It has a sort of a radius, an accretion radius. And it forms when the gas is collapsing, when the energy is negative, so it cannot really be expanding anymore. And it sort of then acts as a reservoir for star formation, which is what we get to now. So if we have a sink, what it will do is it will start to form stars. In my simulation, it will just do this immediately, and it will do this completely. So it's 100% efficient, well, 99 point something. What it will do is it will use the mass distributions in AMUSE, like the Krupa in my case, to say, okay, I have this much mass available, form stars until you exceed the mass that is available. And then it will place them around the center of the sink in a nice random distribution with random velocities that are taken from the velocity distribution of the gas that was accreted onto the sink. So you sort of keep the same velocity distribution overall, but you do a random spread. So this allows us to form individual stars from a sink where your initial resolution may not have been enough to do this, right? You may have one solar mass, for example, per gas particle, but you can form stars that are only 0.1 solar mass. Oh, and the final thing here is that you actually shrink the sink, which means the accretion radius changes. It becomes smaller. And the reason is that you have very little mass left in your sink, which means it could be kicked around and then start to accrete a lot of gas in places where you don't want it to. We also developed an alternative to this. The method that I was just describing tends to work well if you have sinks that can accrete up to about at least 200 solar masses, so or more. If your sinks would accrete mass less than that, like significantly less than that, because they have smaller accretion radii, then you run into a problem that you can't form massive stars anymore, or not enough. So what we did is we said, okay, if that is the case, we try to combine nearby sinks, so that instead of letting each sink act as an individual star-forming region, we combine them and say, okay, these two sinks are actually formed around the same time, they're nearby, they can borrow each other's mass, which means that you don't get exactly the right placement of stars anymore, but at least you don't miss out on massive stars, which is maybe a bigger problem. And this seems to work. So I use this for my simulations of forming massive clusters, or sort of massive. It depends on what you call massive. Like I said, I take initial conditions from a previously calculated galaxy. In fact, we have two different ones that we looked at. These two are the same, except for one aspect, and that is that the potential that we put in to create the spiral structure is stronger in one than in the other. Apart from that, they are the same. So they were calculated from Claire Dobbs, her simulations, and they were simulated with SPH-NG originally. The simulation had originally a resolution of, I think, 311 solar masses per gas particle, so relatively low for my purposes, but relatively high for a galaxy, at least at that time. And they already formed clouds by the time that I am starting to care about them. So you can sort of see that there are these regions that I've indicated with a little bit whiter box. Those are the regions that I care about. So for my simulation, I'm using 1 solar mass per gas particle, which is resampled from the original 311. I'm forming stars with masses down to 0.1 solar masses. No softening, so we can dynamically form binaries. No initial binaries, though. We use this tree and direct embody hybrid for the stellar gravity, and we combine all this with bridge. So we looked at 4 different regions. For the 2 different galaxies, we took on the left side a giant molecular cloud, and on the right side a spiral arm region with a number of smaller clouds. And these we take as the initial conditions for our simulations. The virial ratios of the clouds are like this. So you can see that the orange, which is the giant molecular cloud, clearly a lot more massive than the other clouds, but also seems to be more bound, more strongly bound. Some of those are also bound, but some are not. And it's the same for that one. So these are our simulations. This is a movie, so yes, it should start. So you see that in the clouds the gas is collapsing, and then it starts to form stars, which are the white regions. So you can see, let me repeat that. So you can see that is going on all over the place, right? It's not that it just collapses all into the center and then forms one cluster. There's actually a lot of things going on here. The red circles, by the way, are the sinks. So at some point, a sink may not have enough mass to form the next star. At that point, it will just remain and stay as sort of a protostar, which doesn't... It basically is a star in terms of dynamics, but not in terms of stellar evolution. Here is the same evolution, the same simulation again, but now I'm focusing on one of the clusters. So you can see how this process happens. And you can see that, especially if you look at the one on the right, you can see that there's star formation going on, mostly along filaments and then sort of accreting into the cluster. The one on the left, it's a little bit less visible maybe, but it's also there. So you see that these ones are going to merge at some point. And this is for about 3 megayears in total. Next one is... This is the same, except now we've done a sort of visualization and made it sort of look like how Hubble would see it. Which means that we also take into account that there is gas in front of the cluster, which is obscuring it partially. The main reason for this is just, first of all, it looks nice, but also, we want to see, how would this really look? Of course, we're not taking into account feedback and all sorts of things, but I still think it's nice to make something that looks like this. It's different. We know it's different, but it's nice. The results for these, this is the star and star cluster formation over time. On the left is the stellar mass function for versus time. So you can see that for the clouds, the giant molecular clouds, there's a lot more star formation going on than in the others, which is not surprising, considering how much more bound they were. On the right, you can see the number of star clusters, so the individual clusters that formed. And that it's a little bit more interesting to see there that there was first there were a lot more forming in the standard potential galaxy, but in the end the strong potential galaxy overtook that one. And you see that there is actually a lot more clusters forming in the strong potential galaxy than the other. Whereas the fraction of stars doesn't really matter that much. So this is a little bit more schematic also on what we saw in the movie. We see that these clusters, these are individual clusters here, 4 lines per simulation, that they form in different ways. First of all, there is the regular growth, which is sort of like when you see this line, sort of go like this bit. Sorry, there's a delay here, so that takes a bit while. But sometimes you have this jump here, and jump is caused by a merger between 2 protoclusters. So you saw that happening along these filaments, that they sort of form, and then they're already sort of protoclusters, and then they merge. So we see that happen quite a lot in each of these simulations, and mostly in the clouds. In the other ones, it happens less frequently, and you sort of also see that they level off there. And the reason is just that the gas and the stars decouple more easily there. At some point, there is just no more gas near the star cluster anymore. And then the cluster stops growing. And you see that there's this wiggly line here. That's just because the cluster finder had a little bit of trouble deciding which of the 2 clusters that was about to merge was the main one. We also compared these to observed young massive clusters. So these are data points from, well, I took them from Simon's review paper, but he got them from somewhere else, of course. So these are the open circles. They are observed clusters. The orange ones are the clusters that we think are the most massive, so the ones that I showed in the previous plot. And the blue ones are all the other ones. So we find that our most massive clusters from these simulations actually do look a lot like the observed clusters of similar ages in our Milky Way in terms of the half-mass radius and the mass. So nothing conclusive, there's lots of stuff missing, but it does seem to point in the right direction, which is nice. So my conclusions. I'm a little bit fast, which means more time for questions. So AMUSE is very useful. We have a lot of nice things we can do with it. We've done a lot of things already with it. I've been using it to write this code Ekster, to do simulations of star-forming regions. And the ones that we can form aren't finished yet, aren't real yet, but they look a lot like what we expect to see, which is nice. And now I have time for questions. You don't notice that it's cold here if you're speaking. That's nice. Not yet.
It works. Okay. Thank you very much, Stephen. Very interesting talk. So are there any questions or feedback or comments?
Yeah, in your simulation...
Can you take the micros for the audience?
In your simulation, do you take into account some cooling? Because that impacts the formation of, or the merging of clusters.
We do not. The simulations I've presented here are isothermal. We did look into cooling. We decided that it was a little bit too complex to include here, just for the reason that we want to include as few things as possible initially, because it gets complicated. But definitely cooling, if you want to do the gas properly, of course you have to do cooling, but then you also want to include some kind of heating. Stellar feedback. So we decided it's better to do that in one go. But that is the next step still.
Thank you. Any more questions? Yes.
Hi, Stephen. As you know, I like your simulations, but the question I now have is, what was a scientific question you wanted to answer?
So we wanted to see what's actually the difference between these two galaxies. That was the main original question. So I think from this is really the main thing that we wanted to see. You know, what's happening here? How can we see what's happening between these two different galaxies? So in the end, what we saw is they look quite similar, but for some reason, the number of clusters and the number of stars don't seem to do the same thing, right? The number of the star formation is sort of doing the same thing, but then the number of clusters is not, and I'm not really sure yet why. So that was really the main thing we were trying to look at. Another question was, of course, the more technical one: how do we do these kind of things? And that's also one thing that's still going on. We're going to continue this, but then indeed also include feedback from radiative transfer and stellar winds.
Thank you. Any other questions? I have one myself, actually. So community codes tend to change their interface rather often, and so how does it work then? Is the AMUSE community then adapt their Python codes, or?
So my experience is not that they change quite quickly, not their interfaces. It depends on which code, of course. We have two groups of codes, I would say. One is the group of codes that either have not been in development for a while because they've been stable, so those don't change their interface. And we also have the group of codes that is still under development, and so that will change. In the latter group, it is important that you still have an active participants who are working on both the code and on AMUSE, because otherwise it will get outdated. So we have examples of codes that have become outdated in AMUSE because they weren't just used anymore. But also, at some point, if interest comes back, then we can revive this, and then we can see, okay, has it evolved to the point that we really need to start from scratch, or can we, update what's there?
Okay.
So, for example, for Mesa, we had an old version of Mesa in AMUSE, which was, at this point, 10 years old. Mesa changed its user interface quite quickly after we included that version. So it took us a long time before we got around to updating that in AMUSE.
Yeah. Okay, thanks. Any other questions? Can I first get the youngster?
So in the beginning, I saw you used MPI to communicate between AMUSE and the different codes. Does it mean that you always have a copy of all data in, all the data that you have in your AMUSE environment and in the code itself, or?
No. So you only take what you need from the code. So
Okay,
with
so
a channel, you can say, okay, can you give me the masses of all the particles at this point, for example. So what you tend to do is you tend to make a copy of all the things that you care about.
Yeah, but you don't access the things, because in principle they are already in memory, so you could,
Yes.
look at them, but then you have to.
Yes,
track of the
there is a
states.
way, there is indeed, you could access them directly. There are some reasons why you would not want to do this. The only reason why you would prefer this is if you're really short on memory, but that is generally a case where you wouldn't want to use AMUSE anyway.
Okay. And perhaps a small follow-up question: how did you make the nice visualizations of the thing?
That's also an AMUSE module. We call that Fresco, but it's just a name. But that is an AMUSE module that I developed with Inti Pelupassi. Basically, what it does is it takes a PSF for a telescope. It uses the luminosity and temperature of a star to calculate, okay, what's the color? And then for different color bands, it makes an image.
So could you also use that for, because, yeah, if you have a star, I see how that can work. So can you also do that, for instance, for one of our SPH simulations where you... Oh, okay, nice.
So for an SPH simulation, what it does, it needs a light source, of course.
Yeah,
Right.
then you need to define...
Okay. So if you don't have any stars, it may not be the right code for you.
Yeah. Okay, thank you. Thank you very much.
What are the next steps that you want to take with AMUSE?
With AMUSE,
Uh-huh.
well, a lot of different things. It depends on how much time I have. What I'm doing myself is working to include the Geneva Stellar Evolution Code, GENEC, as an alternative to Mesa. And then we can have a look at colliding stars, for example. That's sort of my own project at the moment. For AMUSE, one of the interesting things I would like to do is make sure that it can run on parallel computers better, so that you don't have one node that controls it all, but that we can split that out. But that's a long-term wish. It has been a wish for a long time, let's put it that way.
Thank you. Any more questions? If not, then let's thank Steven again. Thank you very much.